So today, I'm just going to continue with the Lab 3 that we started looking at last time. And in our last lecture class together, we looked at this exercise 1, and today I'm going to look at and talk about exercise 2 and exercise 3 as well, and we'll see what else we can do in addition to that. Before I jump into that, however, I want to just go over how this grade reporting system works. And Jaron, the teaching assistant for the class, has reviewed your lab submissions over the weekend, and he has rated them based on the criteria and the procedures that I have established with him over the quarters that he's been helping me. So, and I do want to remind everyone about the criteria that's used for doing the grading. It's listed in the syllabus, and here it is. Is the code well organized? Have unnecessary variables and logic been removed from the code? All right, so if you declare a variable called z, and at one point you were using it, but when you finally finish the program, you're not using z anymore, you should remove z from the code. All right, so the idea there is the code needs to be readable. Indentation. Does the indentation show logical structure? So if you have code that's conditioned on a conditional, an if statement, it should be indented to show that that code only executes when the condition of the if statement is true. And consistent indentation. So the indentation should be consistent. If you indent 3 spaces in the first if statement, you should indent 3 spaces in all the if statements. And the purpose of these guidelines is to make your code more readable, so it's easier to read. Logical spacing. Does the spacing show logical structure? So what I mean by spacing is line spacing. If you have two statements, two basic statements and with no space in between them, and perhaps between function declarations you have a line space in there. So at this point in the class, it's not you haven't done a lot of programming yet, so you really haven't had much of a need to use line spacing to show logical structure. But as the size of the programs increase throughout the quarter, you'll find it useful to use line spacing to separate blocks of code to make it easier to read your code and understand what it does. Separation of concerns, once again, that's something that, sorry about that. Separation of concerns is something that comes with a larger program as well. So if you have 2 blocks of code if you have 2 things that need to be done in your program, then it's good to put them in 2 separate blocks of code rather than mixing up the operations together into a single piece of code. It's harder to read that way. It's harder to maintain. Well, that may not be clear to you at this point in the course what that means, but that will become more clear as we go on. And responsibilities. Are the responsibilities of functions and classes clear and consistent? Well, we haven't talked about functions and classes yet, but we will get there. Expressive and clear naming. Does the code contain names for variables, functions, and classes that clearly express their purpose in the program? So if you have a variable that contains, say, a rate of growth, and you call the variable, number of houses. I mean, it's obviously it's inconsistent naming. The name of the variable, although it works, the program may run correctly, but the name that you used for the variable is not expressive of the variable's use in the program. Necessary comments. If a comment is needed to understand the code, put the comment in there. Unnecessary comments. If the comment is not needed, don't add a comment. So if you have a statement that says x equals 1, you don't need a comment that says initialize x to 1. It's too much, it's extra to read. You can read x equals 1. Obviously, we're initializing x to 1. If there's a reason why you're initializing x to 1, that can go into the comment. But don't just say what the code does. That would be an unnecessary comment. Anyway, these are the criteria that we use to evaluate the programs that you write in this class. And this is where the class is currently at. This is and it's ranked. These are the students. Everyone has a secret 2-letter code that you can use to look up where you are in the class. So the person with code FG has 20 points for Lab 1 and 20 points for Lab 2. That's a full score. And these are the total points that those are available for those labs. And so the points earned are 40, and the points attempted are 40. The current percent is 100%. 100% of the available points have been earned, and then the current grade would be, of course, an A. And as you go down the list, you can see that some students are not scoring an A at this point in the class. So we get down here, someone that missed a few points on Lab 2, and other students have listed some additional points on Lab 2, and as a result, the expected grade at the end of the class, if you were to keep that kind of level of performance up through the rest of the quarter, you would end up with, the grade that's listed there. It's a big table. As you look at this, I tried to design it so you could kind of look at the table on your cell phones. That's where I'm headed. If you click a cell, that it'll show you the name of the gradable assignment or quiz. Yeah.
Now, are you doing makeup for any of these assignments? Like, that's anyone? Because I know 17 out of 20. That's pretty close to plus. Are you giving opportunities to go back?
So opportunity to correct your mistakes. I'll tell you, the problem is that that it's too much work for us. Look at the list of students here, and I've had students that I tell them to correct a mistake, and they answer me, well, there's another mistake. Tell them about that mistake, they get back to me. It ends up being too much work. Now, on the other hand, I do accept those kinds of resubmissions, but only in the beginning, and in a reasonable way. Like to say, well, I didn't really read the syllabus carefully. I wasn't aware that you were going to take points off for inconsistent indentation. So okay, go ahead, fix it, and resubmit. Send an email to Jaron saying that you have corrected the mistakes. And but I can't promise that we'll accept late submission of work and rewrites of your work as the course proceeds, because everything should be clear, after the first couple of assignments, what it is that you need to do. So that's with a caveat, okay? So I'm not going to promise a total flexibility on that issue, but that we have, especially in the beginning of the quarter, there's some degree of flexibility in terms of whether you're allowed to resubmit work that's been marked down. Also, you are, if you want to know your code, just look in the email. The email has a that I send to you personally has an extra parameter in the URL that highlights your score, and that parameter is the student ID, and that would be something I say BV, right? So if you request the web page using BV, see. BV is scored. If you know your 2-letter code, you can also, select it from here. That's CV. CV would be there. So that's just to see where you stand in relation to the rest of the students in the class. And hopefully this is going to be useful to you to keep up. All right. Any other questions about the grading? Oh, I do want to say that if you lose points for some reason, like this one, for instance, 17, that Jaron will have inserted into your code a comment, an explanation of why you lost points. And he's going to commit his comment into your repository. That means when you sit down to work, you can do an update operation on your working copy. You'll be able to read his comment. So you'll see exactly why you lost points on your assignment. Okay? So, in other words, you would log into your home directory, CD into your working copy of your repository, which I've been naming CSE 201. Most students are using that name. And then you do SVN update. Just like that. Oh. I'm on JVH 3-1. Okay? Remember, JVH 3-1 is does not have the all the commands that we need. So we need to log into a computer that's in the lab room. So actually, I'm still in that folder. Oh no, I'm not. I have to. I need to go into here and SVN update. So you see, and the SVN command is not available on JVH 3-1. So you need to take another hop, go into some computer in the lab room. So I'm going to start on the second problem of Lab 3. And, without thinking too much, I know that I'll need, rather than try to remember or type in one letter at a time, what's needed to start a new program. I'm going to copy an existing program and use that as my starting point. And here is the, this is problem 1. And so we'll need to redo this. Yeah, just to get started, I like to create a hello program, and there it is. We just to make sure that our starting point doesn't have any syntax errors. Just to make sure that there we go. We print OK. All right, now we have a shell of a solution. And let's go back and look at what we need to do for exercise 2. So we need to write a program that does unit conversion. Write a console program. All of our programs are console programs in this class. They all run from the terminal window. Write this program that converts meters into feet and inches. The program starts by asking for a measurement in meters, And the program should accept a floating point number. After getting the number, the program computes the number of feet and inches equal to the specified number of meters. The program outputs feet and inches as whole numbers. The program should round the number of inches correctly. So if it's something 0.5, you'll round up. If it's less than 0.5, you'll round down. Test that your program produces the following outputs for the given inputs. Your solution to this problem should be contained in a folder called Lab 032. So these are example inputs. If the user types in 0.3049, the output should be 1 ft space 0 in, 1 foot 0 inches. This is the number of meters in a foot, approximately. I'm sure that's approximate. All right, let's. So the program needs to prompt the user for the number of meters, and then display the that number of meters in terms of feet and inches. So let's do it one step at a time. Let's get the prompt working first. Just enter number of meters. And I'm just making a point of this. There's the prompt. We got the prompt working. So look at how small of an increment I just implemented as I'm working towards a solution. Now we'll need to declare the number of meters as a floating point number. So I'll do it like this. And I'll put my variable declarations at the top. I'll put a line space there. I may change that, but for now, that's kind of where I want to put it. Now let's, after we prompt the user to enter the number of meters, let's read the number of meters in. And so we use cin. That's a standard input stream. And the arrows go the other way. We're going to wait for the user to enter in a string, and then this input stream operator is going to attempt to convert the string into a floating point number and store it into the variable meters. The variable meters is declared up here. This statement tells the compiler to allocate 8 bytes of memory to store a floating point number, and we will access that 8 bytes of memory, interpreted as a floating point number. We'll access that in our code using the name meters. That is the name of that stored number. And here, and we're not initializing it here, by the way. So this is an uninitialized number. It might be a good idea to initialize it to some value. Most languages do some default initialization for you when you declare variables. But in C++, that language does not do any kind of initialization by default. So we have to manually initialize. I don't know if 0 is the right number to initialize it to, and it may not make sense to even initialize it, but that's I don't want to get into kind of that debate and analysis, but it is something that's worth thinking about as you start to go through your solution of the program, because normally variable initialization is important. Once we read the meters in, actually, let's just see if that builds. All right, so you're at the very beginning of your learning of this language, so you want to do things in a very incremental manner. Just do one little thing at a time. Get a procedure down so you can do it quickly. Enter the number of meters. All right, and I'm going to enter in this number here. This is the number that I'll test. 0.3049. So far, the program, as it's implemented, is okay. Now we need to convert this to inches and, feet and inches, and then output those results. Now, feet and inches, when we print those will be printed as integers. I'm going to declare those as integers. So I have feet. I'll initialize that to 0 as well. And I'll declare inches. Initialize that to 0. And let's assume in here we'll do the conversion, and then we're going to output the result. So it'll be feet, and then we'll print a space and then FT, and then we're going to print, and we'll have a space after the T, and then we'll print the inches, and we'll print a space and IN. And then we'll print, I'm going to put a new line character in there like that. And I won't use that as a new line character. So in the standard output stream, we're going to print the number of feet that we calculate. Then we're going to print a space, and then the characters F and T, and then we're going to print another space. Then we're going to print out the value of inches that we calculated, and then we're going to print a space and the letters I and N, and then we're going to print a new line character, which makes the console window, drop down to the next line. I'll save that. I'm in VI, by the way, so many of you are starting to learn VI, so I'm going to show you how to do that. This is called command mode, and you actually execute a command by pressing colon, and then it gives the command that's right. So I want to write the file. It shows you down here that the name of the file that was just written, and it says how many characters were written and so on, how many lines, how many characters were written. And let's go ahead and compile and run that. Enter the number of meters, 0.333, like that. 0 feet, 0 inches. We could add some more text if you want, but it's up to you. You say, well, this converts to, or this is equal to 0 feet and 0 inches. You can add, if you want to, dress this up and make it a better output, you can do that. But this is sufficient for me. All right, so we have the kind of the outer kind of shell of the program working the way we want. This is how it's going to look. Now what we need to do is do the conversion, calculate feet, calculate inches. And this is perhaps the harder part, right? So there's going to be a calculation, and then we're going to end up setting the variable inches to something. Now we need a mathematical formula that takes the value that's stored in meters and does some operation on that and produce the number of feet. So that's inches. I'm going to start, I guess inches are all right. I was going to start with feet. Let me start with feet. So what is it? Well, the calculation is going to involve meters. And maybe it's, how many, if you want to convert meters to feet, what do we do? Is that how to do it? I'm just guessing, because I see from my table that 0.3049 meters is 1 foot 0 inches. So if I have 0.34. Imagine this. Suppose I had 0.3049 stored in the variable meters. Then I would have 0.3049 divided by 0.3049. That would give me 1. That would give me exactly what I want. That's 1 foot. So I'm just mentally checking. I sort of took a guess. I used my intuition. What's the formula? And then I went back and I did a mental check. All right. So this is, I don't know how you do it, but we all have to learn how to do this at some point. And so we have the number of feet, but for the number of inches, let's discuss that later. I just want to look at how we calculate feet. Now, this division is floating point division. This meters is a double. It stores a floating point number. In other words, a number with a decimal point. A number with a fractional component. That's what a floating point number is. And why do they call it floating point number? Because the point can appear in different locations in the string of digits. I guess. I don't know. But that's what they call it. It's called a floating point number. It's a number that has a fractional component. So this here is called floating point division because at least one of the operands is a floating point value. In fact, both of the operands are floating point values. So that means the compiler will interpret this operation as floating point division. The very same operator, slash, used with two integers, is interpreted differently by the compiler. In that case, it would be interpreted as integer division. And an integer division doesn't permit a fractional component. It will only produce an integer result. And that'll be important when we calculate inches. But here, we're taking two floating point numbers and we're dividing them one by the other, and then we're going to get a floating point result. In general, maybe in this case, if I type in 0.3049, I'll get 1, but it may not be exactly 1 because it depends on how the computer represents the number using zeros and ones. So this number may not be exactly representable in 8 bytes. Like for instance, a third. You can't exactly represent a third using standard decimal notation. It's 0.3333 to infinity. So you have no way to exactly represent using standard decimal notation the number 1/3. You can exactly represent it as a fraction, 1 divided by 3. That's precise and exact. But if you want to represent 1/3 as a decimal number, you can't do it in any amount of space. It's the same thing, internally in a computer, you have things stored as, you have numbers or values stored as sequences of zeros and ones. In this case, when we have a double precision floating point number, we have 8 bytes. Each byte has got 8 bits. That's 64 bits. You have to is 64 bits enough bits to exactly represent this value? I don't know. I know I can exactly represent 0 or 3 and 8 in 64 bits. It's also how do you represent numbers as well. So there's conventions on how floating point numbers are represented using bits. And there's standards published by standards organizations about how in computer hardware a number is coded in terms of a sequence of bits. So that's why I don't know if I input 0.3049 and do this division, I may actually get a value that is not exactly 1, because internally the computer is truncating and rounding, and it's storing representations of information that is not always exact. All right, but in any case, the result of this division gives a floating point value, but then we're trying to assign the floating point value into an integer variable. The integer variable does not allow a fractional component. So what happens here is that we get some loss of information. For instance, if I type in 1 for meters, if meters were to be 1, then this division results in a number with a fractional component. That result cannot be stored in this integer variable. Remember, up here, feet is declared as an int. That's 4 bytes. An int is 4 bytes. And 4 bytes that are used to represent only integers. Fractional components are not needed. So the compiler will generate machine instructions that effectively grabs the integer part of the floating point number here and drop the fractional component. And it uses a process called truncation. It doesn't do rounding. So if what was on the right-hand side were to be 1.99, if that were on the right-hand side, that would be transformed to a 1. It would not be rounded up. It's truncated. The trick for rounding is you have to add a 0.5. Of course, that would result in 2.499999, like that. Did I get that right? I think I got that right. And this would then be truncated to 2. And 2 is what we normally think of as being equal to 1 point. I'm sorry, I didn't do that right, did I? What's that?
Just
1 extra 9? Oh, okay. But I get that. That's right. So this is rounded. This is truncated. And so we would normally say 1.99999. Well, that's 2, right? So we got to add to get the rounding to work for us correctly. To add 0.5, and then allow that the data type conversion. So it's called data type conversion. We're converting from a floating point value to an integer value. That the standard the standard data type conversion of a floating point number to an integer value does truncation, and so this is the operation we need to get a more kind of natural rounding result. All right, we're going to list the feet here, so let's see what values we get for feet. And also, by the way, this meters could potentially be a lot bigger than this int. So the compiler is either going to fail to compile this, or it's going to give us a warning. Or it won't say anything. So one of those 3 things. It doesn't say anything. Okay. Number of meters, 0.3049. Now if we get a 0, it's possible we can get a 0. We don't get a 1. Okay. Let me run it again. Number of meters, 1. I said 1. So now the input is 1, so we should get 3 feet, 3 inches, because we'll ignore the inches part. But let's see if we get the right number of feet. 3 feet, we got that. All right, let's run it again. We'll try it with 2 meters. 6 feet, yeah, we got that. The test data, we're confirming with the test data. We got 3 values given to us with the test data are now working correctly. All right, now the next task is to get the inches computed. how do we calculate the inches? So we have the number of feet. How about if we do it like this? I'm just going to think about this. We take meters divided by 0.30, and I'm just going to, I don't know the answer, I'm just going to sort of figure it out. I'm going to start by calculating I'm going to convert, this expression here converts meters into feet. So, but it has a fractional component, before doing the assignment. So this is a fractional component. So let's multiply that by 12 to convert from feet to inches. So now we have total number of inches. So this gives us the total number of inches with a fractional component. But it's not good because, well, we want it to be rounded because we're going to truncate, right? So this gives us total number of inches, rounded. This is not the answer. This is only halfway there. Number of meters is 1. 39 inches. This is total number of inches in 1 meter. Is that right? Are there 39 inches in 1 meter? Anybody know? That sounds right. Okay. Well, now what we want to do is we got to take out 3 feet. So we're going to take out 12 and then 12 and then 12. We're going to take out 36 because 36 of the inches are already, contained in this value here, which is feet. We're going to take out 36 inches. How do we take out 36 inches? Well, we're not going to do that, right? Because we could enter a different number. So how do we get the 36 inches? Well, we take the number of feet and we multiply by 12. That's how I did it. I said, oh, there's 3 feet. I've got to multiply by 12 to get the 36 inches. I think that's going to give it to us. Three feet, 3 inches. And look, the test code works. Works with the test code. Let's try it with 0.3049. That works. Let's try it with 2. We got it. If we're happy with that test code, then we're done. If the test code, if the test data rather, if the test data is inadequate, then we're making a bad conclusion at this point that we're finished. That's it for this problem. Does anybody have any questions about this?
I have a question.
Yeah.
Can you just use like a conversion factor?
Well, isn't that a conversion factor right there?
Right, I know, but like that's just like from feet to meters.
Yeah, so we could use meters to inches. Yeah, we could use different conversion factors for sure. We could use meters to inches, definitely. I didn't like this because I just see the test data and I know I got to get 1 foot there, so I might as well just use that number and get that foot. So I sort of derived the conversion factor from the test data. But this number isn't quite exact. Does anyone have a better number than this?
The 9 should be an 8. It's the same thing.
Are you sure? What comes after the 8?
1 meter equals 3.28084.
1 meter No, no, I know. 1 foot. What does 1 foot equal in meters? Yeah, if you start with 1 foot, how many meters do you get? So I think I have.
0.8. Oh, well, come on, that's not working.
Isn't this the way that you do it? This is how I do it. Isn't that incredible? You're right, it is an 8. It's not a 9. I put a 9 in there. Is this it exactly? You know, maybe the test code is bad. So this should be 9. And I'm going to get rid of this comment. Also, this comment doesn't do much for me. I'm going to take that out. But I like these line spaces. You see the line space? This is just variable declarations. Then I have a little space there. Then I want to get my meters here. Then I do the calculations and I output the result. You see the logic in that line spacing? That was very deliberate. It wasn't just happening. I deliberately created that line spacing right there. And look at the indentation. Everything lines up, you know. I don't have it doesn't look like this. You see that? That's a lot harder to read, isn't it? So you'll get points taken off when you submit programs that look like that. Let me show you. Here's another. I'll show you how you might incorrectly get your line spacing. What if you did this? What if you did your line spacing like that? Does that line spacing make any sense? So you're going to lose points for that. This doesn't make any sense. It doesn't express anything. It doesn't help with the organization at all. In fact, it creates confusion. This structure of the code is very important for readability. And you'll see skilled programmers are very, very careful. Every single space, every point is just perfected. I mean, not always. There's a deadline and you're racing through and you're working with sloppy code and you just slap in a solution and get it to run and build. Yeah, there's those situations as well. But certainly if you have a skilled programmer who's going to be, say, presenting their code to other people in a code review or in a presentation, the code is going to be absolutely perfect. Okay, so let's see, this is an issue here. Maybe the test code is not going to, the test data may not look good now. Say it again? Yeah, you have to add the 0.5. You have to do the rounding in any case. That's right. The 0.5 does the rounding. All right, I'm worried about this. So I'm going to move on to the next problem. But this is going to delay things if it doesn't match the test code. All right, 0, let's do 1 here. It works. 2 is okay. And 0.3049. Oh, I see. This is a little bit bigger than a foot, but it's not big enough to make a whole extra inch. Good, that works. Very good. Thank you for that. And so the conversion factor, this was a poor choice for conversion factor. That's just the test data. In fact, I could have entered even a slightly bigger number, and it still should come out to 1 foot and 0 inches. 3, 0, 5, 1, for instance. That still gives me 0 inches because I get a value that's smaller than ½ an inch. So I'm going to round it down to 0. All right, I was sloppy. Thank you for suggesting to use the correct conversion factor. That is, in fact, what we needed to do there. And my solution using a 9 was incorrect, and this is correct. Okay. The last thing we do, I'm going to add this to the repository. Please remove the a.outs before you do an add operation. We don't need that in the repository. And then I'll do svn. Notice I CD'd up to the root of the working copy of my repository. So that's the place where normally you want to do these subversion operations. So we've scheduled to add the folder itself, lab 032, and we've scheduled to add the main file within it, but we need to commit. But before we commit, we could check. I'm not going to do that, but well, just to emphasize the point, I'm not going to do it. Remember, you should check with the web that that your commit works. Look at that. And I'll check in a more I'm going to check in a scarier way. Well, I'm going to show you how I'm going to check this. I'm going to delete all my work. Look at that. I just deleted everything. I didn't delete that control file there. It's got the information in to go to the repository. And just do an update. I got everything back. Isn't that nice? All right, so I could be working on another machine. I do a checkout, do an update. I can synchronize against the repository. All right, so that's that. Let's go ahead and look at the third problem in Lab 3. Once again, I'm going to copy the previous code and use that as a starting point. One thing that I didn't do, by the way, what happens if we put an invalid number in there? And I didn't ask for that. So that's another topic. How do you check for invalid data entry from the user? So that's not, I don't ask for that in the program. Do I? Do I ask for that? No, I don't ask for that. I'm going to omit that. But normally you would need to, what's called validate. You would need to validate user input. And if the user input is not valid, you need to give the user, you need to tell the user that the data input is not valid. And then ask the user to try again. So we have not done that. Maybe I need to change the exercise for next time I teach the class. I don't know. All right, so let's go to exercise 3, random numbers. Before I read that, I'm just going to try to get ready early here and clean this out. We don't need this part of the program. Write a program that generates a list of 100 random integers. the C++ standard library contains a pseudo random number generator that you can use to solve this problem. The function rand returns a pseudo random number. To use rand in your programs, you need to include the cstdlib header as follows. So we need this. Oh, I had CMath in there. Did I need CMath? I didn't need CMath in the other program. And I don't know if I need string in there. I probably do. That's the header that we want. Now this CMath library, I don't think I need that. I might need that. And by the way, oops. I need to clean that up. We don't need CMath in here. I'm not using anything in that header. Actually, I don't believe I'm using anything in this one either. Let's test that it still runs. That's good. So I'm going to commit that change. So once again, that don't include things in your program that are not being used. I copied over that code from another program, and I should have examined those include statements to see that I didn't need them. So I don't think we need this string either. Take that out. The function rand will return the same sequence of values for a given seed. You can change the sequence of values it returns by changing the seed as follows. srand, that means seed the random number generator. Anything, you can put anything in there. The following example shows you how you can use the return value of rand. Rand is a function, and we call the function using these parentheses. So you have the function name, rand, and then you have information that's passed into the function. That information is called arguments. This function takes no arguments. And so we simply have a list, which is delimited with parentheses. We have an empty list because the rand function takes no information. The rand function returns a value. The value that it returns is what we're passing into cout. Let's see if this code runs. That's the result right there, and that's hard to read because I need to print a new line, which I'm going to do with that end line constant. There's the number. Look at that. What kind of a random number is that? It's the same random number. That's because rand, as I stated in the instructions here, rand returns the same sequence of pseudos. It's called a pseudo random number generator. It's not a real random number generator. It will return the same sequence of values for a given seed. if we change the seed, even by a little bit, we're going to get a completely different sequence of values. Well, once again, it's the same thing. So this is our old first value in the sequence. This is our new first value. You know, what happens if we print 4 values? These are the first 4 values of the sequence that's associated with the seed 998. There it is. This is the first 4 values in the sequence associated with the seed 998. So if we run the program, we're going to get the same 4 values. It's the first 4 values in the sequence. So that it's not really. Let's make it a little more random. Well, when we seed the random number generator, let's pass in an argument, a different number each time. And time 0 is a convenient way to do it. So let's do that. Time is a function, and we pass in a 0 here. And what this time function does when you pass in a 0, it gives you the number of seconds that have elapsed since some epoch. Epoch is a point in time. The standard epoch is January 1st, 1970. You see that in a lot of Unix systems. They use that particular time, moment in time, as a starting point for time values. But I think Windows may have a different value for that. It's not, you know, what time 0 returns is not. It's not a part of the standard. Now this function here, so this is the number of seconds that have elapsed since 1970. So if I compile the program, if I run the program 2 times really fast within the same second, I might get exactly the same result. So there's that danger. Now I think there's a header that's needed for this. Do I mention that in here? Let's see if it doesn't. I don't mention the header file. Let's see if this builds. I'll clear that. It builds. All right. There is the first 4 integers in the sequence of values associated with some seed, which equals the number of seconds since 1970 when I ran the program. If I run the program now, the number of seconds since 1970 is a little bigger. So I'm going to get a different sequence of values. So that's one way to get some randomness there. Now, you know, actually, it's an interesting topic. I'm not going to get into it deeply, but it's random numbers are very important and required to do encryption for security. So when you do information exchanges on the internet, that the internet is kind of this wide open place, and then your data that you send from one computer to another computer has to pass through many systems that are managed by different organizations and different people. And there's going to be people that have access to those intermediate systems who cannot be trusted. And so you don't want to send credit card information and other sensitive information unencrypted, you know, through untrusted systems. And the internet is untrusted, 100%. And so you need to encrypt it. But those encryption procedures rely on the ability to generate random numbers. And you would never use the procedure I'm showing you now to generate random numbers because it's simply predictable. Like, oh, I'll just try values, you know, which, you know, I'll just iterate through all the different possible seconds since 1970 that occurs right around now, and then I'll hit the sequence that you end up using to encrypt your credit card data, and then I'll be able to decrypt it like this. So it opens up a security hole. So when you do encryption, when you rely on random values for the purpose of data encryption, you need to use a secure random number generator, and that's another topic, of course, on how to accomplish secure random number generation is actually, you know, a deep, you know, concern and topic, and has taken a lot of study. All right, that's enough on that. Let's go back to the program. Use a for loop to generate the 100 list item entries required by this problem. You can save the program output by redirecting the standard out to a file. Okay, I'm going to skip. I'll come back to that in a minute. Let's get that for loop in there. We need a for loop. It looks like this. For integer I initialized to 0, for as long as I is less than 100, do the loop, and then at the end of the loop, increment I. That's how you read that. That's called a for loop. That for loop in C++ is exactly the same syntax you would use in Java, C#, JavaScript, and many other languages. It's a very standard kind of syntax. Whereas cout, you're not going to see that in any other language, except maybe C. No, you don't see it in C, sorry. I don't think you see that's part of the C++ standard library, I think. And so this is a for loop. It has 3 parts in it. And the parts are separated with semicolons. So you have the first part, and then you have a semicolon. That's called a delimiter. The semicolon is a delimiter. Delimiters separate 2 areas from each other. Then you have that second area. Then you have the third area. So you have 2 delimiters to create 3 areas. And then the first spot here is initialization. This is run once at the beginning of the loop. So when execution, when the program runs, when the computer runs your program, you just think of it as going down one statement after another and executing each one. Now here we're interrupting the normal flow. We're saying, oh, don't just go automatically to the next statement. We want you to sort of repeat this block of statements here. Well, there's only one statement in there now, but it could be many statements. Repeat this block of statements as long as the loop condition is true. The loop condition is in the middle part. I is less than 100. That's called the loop condition. If the loop condition evaluates to true, the statements that are in between these parentheses, between these braces, we call that the loop, the body of the loop. As long as the loop condition is true, we're going to execute the body of the loop. Execute the body of the loop, check the loop condition. If it's true, execute the body of the loop and check the loop condition. If it's true, execute the body of the loop, check the loop condition. Loop condition's false. Well, at that point, we're going to go on to the next line, which would be whatever it is. So you do this. But that's a simplification. Check the loop condition. If it's true, do the body of the loop. Well, let me add some details there. It's not all it does. Check the loop condition. If it's true, do the body of the loop, and then do the end of loop operation, which is the third space here. So as soon as we complete a pass through the body of the loop, we're going to execute the code that's in this third area, which is, and this code says plus I, it means increment I. I is an integer, add 1 to I. Make I 1 bigger. So if I were 3, And when we execute plus I becomes 4. Now the only, and to remember, I did mention this, but when execution passes down and hits the 4 statement, the first thing that's done is the initialization section here. An integer I is allocated. It is initialized to 0, and that's done once. It's done at the beginning of the loop, it's done once. The things that get repeated are the loop condition, the end of loop operation, and then the body of the loop itself. The initialization section does not get repeated over and over again. It's only done once. And you see, you set I to 0, so look at the loop condition. Right off the bat, the loop condition is true because 0 is less than 100. Oh, okay, the loop condition is true. That means I'm going to execute the body of the loop. So I'm going to print a random number. And then I'm going to increment I, so I becomes 1. What do I do after I increment I at the bottom of the loop? Well, I come back to the top of the loop, and at the top of the loop, I evaluate the loop condition. So now I is 1. 1 is less than 100. The loop condition is still true. That means I'm going to execute this. This will continue until I hits 100. When I hits 100, at the bottom of the loop, we're going to do this plus I. If I were 99, and we increment it to 100. And then we come up here, and we compare 100 to 100, and that loop condition is now false. 100 is not less than 100. We start at 0, we go up to 99, and for 0 to 99, we do the body of the loop. That's 100 times. We do the body of the loop 100 times, because we start at 0, we don't start at 1. That's by convention. And as soon as I becomes 100, and we're done with the loop, and we're going to print OK. Let's see that work. There it is. We should get a different string. There's 100 random numbers. You can save the program output by redirecting standard out to a file. To do this, run the program in this way. Open numbers.txt in the text editor to see the result. This is called redirection. We're redirecting standard output to a file. Standard output, if we run the program like this, standard output is no longer the console. Standard output is now the file numbers.txt. And you see that that's not there, but look, numbers.txt got created. Let's take a look at what's in there. There it is. There's 100 random numbers. That's an example of redirecting to reassigning standard output to something other than a console. And that's it. We got through Lab 3 today. And so that's all for today.